Hello everybody and welcome to another week of distance learning. I'm gaining more and more respect for those of you who do videos with Mr. Hurst. I literally just shot this whole thing, and when I went to check it, I filmed all of it in slow motion. So I don't know what I did wrong there, but hit the wrong button, so it was all in slow motion. So here we go again. As you can see, I've got the dynamics card out. We're going to have a lab posted for the physics class on Friday. Been working on that for a couple of days, and I hope it's an interesting lab for you. It goes along with all we've been studying about work and power and forces and how they all interact with each other. It's a good lab. I wish you got to do it, but again, we'll have that on Friday. I've set up my little studio here. As y'all know, Seth is in the Army and he's at Fort Benning, and he's kind of sequestered there. He can't come home, can't do anything. He's sort of trapped in Fort Benning. And I've set up my little studio here in his bedroom, which is just full of interesting things. Story after story after story can be told just by the stuff in this room. And I'm going to show you the most interesting story today. But to do that, I've got to move around and move the camera a little bit. So if you get motion sick, you might want to close your eyes because I'm going to swing the camera around for just a moment, let you look at something. So here we go. We're going to take a quick little turn. Up. See right there on the ceiling? See that little thing right beside the ceiling fan? Well, we're going to discuss that for just a moment. Let's go back down to normal. That'll be... Whoa. That'll do it. Anyway, well, we've lived in this house now for 22 years. As a matter of fact, it's the only house... We moved in right after Seth was born, or right before Seth was born, I mean. So it's really the only house he's ever had. And so like I said, this is his room. It has been his room all these years. And when the boys were younger, they had a lot of Nerf guns, just a little fun. We have hundreds of these just laying around the house. Well, about probably 13 years ago or so, one of the boys shot that Nerf dart onto the ceiling. And it never fell. And they would shoot them up there all the time, and they'd stay up for an hour or so, and then they'd fall. Well, that one never fell, and it was sort of a running joke for a week or so, and then it went to a month, and then it went to a year, and now it's been about 13 years that dart has been stuck in that exact same spot on the ceiling. Misty has threatened to knock it down on more than one occasion, but thankfully leveler heads have prevailed, and the dart is still there. No idea how long it's going to stay up there. Personally, I don't intend to ever knock it down. If I'm 80 years old and coming through the house, I'm always going to look up and see the dart and remind me of the boys when they were young and just playing here at the house. One other little update for you before we start today's lesson, and that is my running challenge I've set for myself. Today is the day I'm filming is Sunday the 19th. As of right now, I ran this morning. As of right now, I have 61 and a half miles in for my 100-mile April challenge, so it's going right on schedule. If I stay exactly like I'm doing now, I will hit 100 miles on the 29th, the day before my birthday. Other than that, things are well. I hope you're doing well. I hope that you are maintaining some semblance of sanity in your sequestered life that you're living now. I hope that you're, again, focusing on this whole routine thing, but I hope you've got a routine going. I hope that you have, set yourself your own challenge. If you've got some kind of a challenge, post it in the classroom just as a comment and tell us, hey, this is my personal challenge for the month, what I'm working on. Just again, for entertainment purposes for the rest of us. I hope you enjoyed today's lesson, and I hope to see y'all soon. Okay, everybody, today's lesson is on power. Power, by basic definition, is just a measure of how quickly work is done. The faster you work, the greater the power. Best classic example is running up a set of steps. If you walk up a set of steps, low power. If you run up the same set of steps much faster, more power. Formally, we end up with this formula right here. Power equals work divided by time. For those of you that like the triangle, let me draw you the triangle here. That would give you this triangle right here. Power equals work divided by time. The SI unit for power, work, remember, is in joules. Time is in seconds. So joules per second is called a watt. So we have the formula, work divided by time, where the work has to be in joules and time has to be in seconds. Let's take a look at example number 1. We have Max here doing 137 joules of work in 1.2 seconds. What is Max's power output? You can pause the video for just a moment if you want to work it and start it back up. This one is about as straightforward a problem as you're ever going to run into. Oops, there we go. Don't know why that does that. Power equals work divided by time. The work is 137 joules, so I have 137 joules divided by time of 1.2 seconds. Take my trusty calculator here. Take 137 divided by 1.2, and I end up with 137 divided by 1.2. I end up with 114 watts. 114 watts. Here we go. Take a little look-see at problem number 2. Mary slides a box with 72 newtons of force at a constant speed of 4.1 meters a second. What's her power output? Now this one is not straightforward, and it is still a classic problem, but it's not a straightforward, easy problem. So what I want you to do is I want you to pause the video again. I want you to take a few moments, and I want you to try to work this one and then start it back up. Okay, well, we know if we're looking for her power output, then we know we've got to end up with power equals work divided by time. Well, work is not given in the problem. We've got 72 newtons and we got a velocity. Well, work is force times distance. Well, I've got a force, so I know I got my 72 newtons, but I don't have a distance, and I don't have a time. So this is kind of oh no, I can't solve this one. I don't have time. I don't have distance. I mean, all I've got is a velocity. Well, we know what velocity is. Velocity is distance divided by time. So we make an assumption. So there's my distance. There's my time that I need for these two formulas. If I make the assumption that the power output is over some time interval, then I can work the problem. Well, the time interval I'll use is 1 second. If I just let the time equal 1 second, then everything will just fall into place. So her work is her force, which is 72 newtons, times her distance. Well, in every 1 second, she goes 4.1 meters. So I go 4.1 meters in that 1 second. So I have 72 times 4.1 gives me 295. Let me double check that. 72 times 4.1 gives me 295 joules of work. Well, drop that in over here. 295 joules in 1 second is 295 watts. So as you can see, even though the problem doesn't read initially as a simple problem, it is a pretty straightforward, pretty easy problem once you take a look at it. One little side note we want to give you here, and you can take a look at this slide. Again, I'm not going to read the whole thing to you. What we're going to say that is most important is watts is the SI unit for power. It is not the normal unit that you'll hear out and about as you move around. And that normal unit you hear is a horsepower. And 1 horsepower is 746 watts. We won't have any actual problems that we do that you have to worry about that, but I didn't want you to think that watts was the only way of measuring power when you normally will hear it out in the world as horsepower. Typically, people can deliver at most 1 horsepower is about how much a normal human being can deliver. As a matter of fact, the example that we talked about a minute ago about going up a set of stairs, if you run up a set of steps, a normal 1 flight of steps, it's going to take you about a quarter, maybe a sixth of a horsepower to do that. So you can see that's not your full exertion, so you actually can give off a little bit more power than that. But a typical human, 1 horsepower is about what you can produce. Take a look at this problem. I'm going to leave this one with you. I'm going to let you work it. And this problem, I'm going to try and solve it. You can put the answer into your video acknowledgement form if you want some bonus points. And other than that, we're going to pick up on this problem on Wednesday. Thank you.